Physical Sciences, Lesson 18. Topic: Electron interactions, multiple bonds, oxidation state, molecular shape and conduction. Turn to Lessons 17 and 18 in the Learner's Workbook. Integration. This lesson integrates with life sciences, molecular biology, mathematics. Molecular shapes relate to any work in geometry involving shape. Prior knowledge, grade 11, lessons 15 and 16. Lesson overview. In this lesson, you will discover the behavior of electrons in solids like metals. Learn about an interesting and important category of materials that lies between metals and non-metals called semiconductors.
Hi and welcome again to our physical sciences lessons. It's Tinyiko Machabikosa.
And it is welcome back, of course, from Peter Glover as well, because we're going to continue where we left off last lesson. And there we were talking about the importance of the shapes of molecules and how this can actually affect the way molecules react with one another. We're going to start with an idea that has a very fancy handle. It's called VSEPR.
And that stands for valence shell electron pair repulsion.
Okay, now notice, listen to it carefully. Electron pair repulsion. We're talking about the repulsion between electron pairs, because once electron pairs have been established around an atom, electrons are all negative. They are going to repel one another. And how they repel and how far is going to give us some idea of shape, and we're going to show you how that works.
And it also says valence, and therefore we are specifically talking about those outermost electrons. We're not so concerned about the core electrons.
Valence electrons are very important for all sorts of reasons. Now, the first thing we've got to do when we look at a molecule is we've got to look at what valence electrons are operating in that molecule. What kind of valence, or what number of valence shells, valence electrons have we got? Let's take an example. CH4. Now you will remember that is methane. We dealt with it last time.
Last time it's methane, CH4.
CH4. Now, carbon, you remember, had 1, 2, 3, 4. If we drew our Lewis diagram, so carbon had 4 valence electrons. Valence electrons. Each hydrogen, and there are 4 of them, has 1. So in other words, altogether there are 4. Okay. Now that kind of calculation will be very important when we start working out the shape, and we are going to take something that is even more familiar to us than
the methane molecule.
We're going to take water, H2O. We are going to introduce you to a worksheet which you can use. You can copy it down. You can use that in order to do VSEPR calculations. And here it is. Now, this worksheet for doing these calculations starts off by asking what is the molecular formula. Now when we talk about the molecular formula, we're talking about the number of atoms in a molecule.
Different atoms, of
and
course.
We're also talking about the ratio
in which they
combine. Okay, so for water, of course, H2O, 2 hydrogens, 1 oxygen. Hydrogen to oxygen in the ratio
of 2 to 1.
And of course, when we write this down,
H2O,
the molecular formula that we write down gives that to us automatically. Now let's draw the Lewis structure, and let's do it this way. We've got 1, 2, 3, 4, 5, 6. We've done this before, so we know what we're doing now.
Bring in the H atom there and the other H atom over
And remember, we said that constitutes one bond, that constitutes another bond.
Yeah.
Now, Okay, let's just talk about that. We've seen the picture. Just looking at that, what would you say was the shape of the water molecule?
By mere looking at the diagram that we have, one can be tempted to say we're going to have a linear type of shape here.
A linear molecule.
Yeah.
Oxygen in the middle, one little hydrogen, another little hydrogen, straight
Linear.
line.
Yeah.
That's what it looks like. Let's see why we do VSEPR, because, let you into a secret, it's not quite that. Right. Good, Tanika. Let's have a look and see how this all works out and see if this calculation is going to tell us anything different from what we suspected intuitively. Right, here we go.
The molecule is H2O.
And that is what is called the molecular formula, and it gives us a lot of information. It tells us what atoms are in the molecule, and it tells us the ratio of the atoms. So we see here 2 hydrogens to 1 oxygen, ratio 2 to 1, 3 atoms altogether. The Lewis structure, well, we're getting pretty good at this now. And so we've got 1, 2, 3, 4, 5, 6, and the hydrogens coming in here. And so here we've got one bond and another bond. We could actually show it like that, H-O-H. And as you said just now, it looks pretty well as though that is
linear.
A linear molecule. Okay. Now, the central atom is clearly oxygen. And we know that oxygen has these 1, 2, 3, 4, 5, 6 electrons. We know that the number of atoms attached to the central atom
is 2 hydrogen atoms.
2. The valence electrons on the central atom, 1, 2, 3, 4, 5, 6. Okay. The valence electrons from the attached atoms. Now we've got to be careful.
So we've got 2 of the
hydrogens,
atoms, so it's 2.
Each contributing
1. So it will be 2.
2 altogether. There they are. Okay. Now, the total number of electrons is 8. And if we divide this by 2, we get the number of electron pairs. And we find it has 4 pairs.
Yeah.
Now, here we have 1, 2, 3. I think you can see there 1, 2, 3 pairs and a 4th pair. So there's 1 pair there, 1 there, 1 there, 1 there. Now, if we've got 4 pairs, and forget now that of these pairs of, let's say, this pair, 1 comes from a hydrogen and 1 comes from the oxygen. That doesn't matter. The fact is we've got 4 pairs. Now, these are electrons.
And they are negatively charged.
They're negatively charged. That pair and that pair will repel
each other.
So will those 2 pairs. So will those 2 pairs. So will these 2 pairs. And there are repulsions between all the pairs. Now, if we think about it, nature is symmetrical. Nature likes balance and symmetry. If we've got 4 electron pairs around here, and I think I've just lost an electron. Yes, lost one. Don't want to do that. Okay, we've got 4 electron pairs. They're all repelling one another. All the electrons have got the same charge on them. So the forces of repulsion are the same. How will those 4 pairs distribute themselves around that sphere?
They are going to distribute themselves in such a way that they are equidistant from each other. In other words, the distance from one electron pair to the next is equal to the distance from another electron pair to...
Another way that we could say that, not just equidistant, but equidistant would mean that things change when we go from one size molecule, one size atom to the next.
To the next,
Let's rather say equiangular. The angle between that and that, and that, and so on, the angles are all the same.
All the same,
Now, I'm going to show some pictures, and we can have a look at this and just see what these angles mean.